So here we are. They will concern first the exploitation of high-dimensional dynamic state spaces for computation. They differ very much between natural and artificial systems. They will also concern sources of the internal model of the world, sources of information to instruct this model. Then internal value assigning systems that do exist in natural systems and not so much in artificial systems. And finally, the option to generate a self-model through the embedding in a social-cultural environment. So now you can go on with the digestion cycle because this is the summary, more or less. So the two systems, they use very different strategies to encode relations, semantic relations. And why do relations matter? Because of the composite structure of the world. So the virtually infinite number of different objects in the world around us is generated by the combination of a limited number of components. And these components are assembled in hierarchically structured networks of nested relations. So any cognitive system is well advised to invent mechanisms for economical representation of this diversity of objects. So there are two complementary strategies for the description of objects. One is an explicit representation of all possible objects by specialized representational units. Now this leads to a combinatorial explosion because you would need one unit for every conceivable object in the world. The other possibility is to have explicit representations of the components by individual units, but then have an algorithm for flexibly encoding relations among those objects in order to establish a combinatorial code. Much more economical, much more difficult to realize. So how are strategies, what are the strategies for the establishment of relations among components? One option is to represent frequently occurring constellations of such components by chunking. I will give you an example in a minute. And the other is to dynamically associate the components by a flexible binding mechanism. And for the chunking solution, we know that virtually all natural systems exploit it, and most artificial systems, in particular the deep learning networks, they follow this strategy. It consists essentially of hierarchical feed-forward architectures, as shown here in the classical perceptron architecture, where you have input units, here designed as A and B, responding to particular components, A and B, or features, that distribute their activity in feed-forward pathways onto another layer of nodes. And from this layer, you have another set of converging connections to conjunction-specific units. And by adjusting the gain or the weight of these connections, one can achieve that an output unit, like this red unit here, gets active only and only if a particular constellation of components A and B is present in the outer world. This is essentially the strategy that is used by all the deep learning convolutional networks. It's just scaled up. There are many more layers, up to 100 or so. And what one does is one shows these networks at the input layer a activity vector, a pattern, and then adjusts through a very artificial computational algorithm called backpropagation algorithm the weight distributions of these feed-forward connections until one gets at the output layer a one-to-one correspondence between the activity of a unit and an input pattern. And this learning process requires a huge number of iterations, millions of iterations, before the network can really classify properly a particular input pattern by the activity of a particular output unit. So this is a safe strategy. It is not very dynamic. It is mainly linear and has severe limitations because it's extremely hardware expensive. And also the training is very cumbersome. It has no associativity, which is a big problem if one wants to establish, in particular, relations among objects that have been recognized. And if one thinks about nested relations, hierarchical relations, it becomes even more complicated. So the solution is, of course, and this is what nature has opted for, is to represent composite objects by the dynamic association, or the binding as others call it, of the components. So units representing components or chunks are formed, but then these units are bound dynamically into coherent wholes, into so-called assemblies. And this requires reciprocal interactions. So in this case, the units A and unit B interact with each other and form a descriptive whole for the composition A and B. In this case, C is added. In this case, D is added. One can have an ensemble of all four of them or only parts of them. And this can be, in a very flexible way, recombined to express virtually all sorts of relations among those components that are possible. Language is a great example of this coding strategy. The 28 symbols of the Latin alphabet suffice to compose the world literature. And the strategy is exactly the same, a hierarchical grouping of elementary components, in this case the letters, into phonemes, into words. These are the chunks. And then those chunks are associated in a flexible way into sentences and narratives using grammatical rules or syntactical rules. So this coding strategy is a hallmark of natural systems, but it does require a different architecture. It requires recurrent connections among the coding units. And it requires, in addition, as I will show in a minute, dynamic signatures that allow one to label the units that are temporarily assembled into one of these representing wholes, these assemblies, as belonging to this assembly. So we know that the implementation of recurrent connections is found everywhere in nature. A very characteristic feature of the cerebral cortex, for example, what you see here is the green pyramids. They are units in the cerebral cortex. They are partially representatives of components or chunks or individual features, but these units are reciprocally connected through these red connections, a huge network, very densely connected, that makes up for about 80% of the contacts that are made on these units. So they all reciprocally interact with one another, producing a very, very complex dynamics. This principle is scaled up. What you see here, maybe you can't see it nicely, is a connectomic graph of connections among cortical areas in the monkey brain that deal with the processing of visual information. All the red dots you see stand for a cortical area, which contains billions of neurons. And these areas are connected among each other, i.e. the neurons in these areas are connected among each other through these white lines. And you see this immensely dense network of connections that reciprocally connects these units in the different areas with one another. So they all interact with one another. If one knows one's way in this map of underground connections, one or two switching stations are enough to get from anywhere to anywhere. So the prevailing principle here is parallelity, is reciprocity of interactions, and is flat hierarchy. It's very, very different from what you know from deep convolutional networks, for example. So a Gedanken experiment, imagine such a system, and this here is the graph of the sensory cortical areas and their connections in a cat brain. And I only show the auditory areas, the visual areas, the tactile areas. They are black dots now in this case. And limbic areas on top of the graph. Those are areas that add emotional connotations to the computational results that have been obtained in these other areas. So whether the object that one has recognized is something that is menacing, or whether one should have a peaceful interaction with it, whether it's good or bad. So now imagine that such a network, and we have the same network in our brain, except that it's about one order of magnitude more complex given the number of areas, is exposed to a polymodal object like a barking dog, for example. Then billions of neurons in these various areas will become active, those neurons responding to particular features of this particular object. if you touch the object, the tactile neurons will become active. If you look at it, the visual ones, and if the dog barks, the auditory neurons. They will all be simultaneously active, and through these reciprocal interactions, create a spatio-temporal cloud, an extremely complex cloud of activity that is the not further reducible description of this object. So this object is not localized somewhere in this network. One cannot pinpoint it. It is a distributed representation and cannot be further reduced. It's a spatio-temporal, very high-dimensional pattern of activity. This is the representation in our nervous systems of a concrete perceptual object. Now imagine that there is a second object, like a cat, next to it. There will be a second cloud, and these two clouds will be interdigitating in time and in space. And therefore we need a signature that allows the rest of the brain to find out from moment to moment which of the many activity responses of the neurons actually belong to which assembly, to which cloud. This is addressed as the binding problem, a problem that will emerge sooner or later also in artificial systems. We aren't there yet. And it's very much related to the problem that you have when you segment a complex scene. In this case, in order to identify these horses on the picture, what the system has to do is to associate the right black surfaces with the white surfaces that all together make up for a figure. And we do this effortlessly. A big problem for artificial systems because they have no real concept of an object to begin with and of Gestalt criteria. So we need a signature that relates the responses that code coherently for a particular object, a cognitive object. A natural signature is, of course, temporal synchronicity, because things that occur simultaneously with all likelihood belong together, and if one follows the other, they may be causally related, and if they're completely uncorrelated, there seems to be no relation. So this mechanism is used by brains. Temporal structure is generated by a mechanism that makes that most neurons and microcircuits have a propensity to oscillate, also something you don't find in artificial systems. And these oscillators are reciprocally coupled to the connections that you have seen, these red connections. And coupled oscillators, of course, have a high propensity to synchronize and to assemble each other. They attract each other. It's the basis of attractor dynamics. So after successful segmentation of these assemblies, you would end up with a state where neurons coding for, it's a very simplified interpretation, for the first horse, the green ones would produce correlated activity, and likewise the neurons coding for the red horse would do the same, but the two would be uncorrelated. So the two assemblies can be separated in time rather than in space, because spatially they will be overlapping. Now, once one has recurrent connections in a network, novel properties emerge, and they can be exploited for computational strategies that are extremely efficient and can solve some of the problems that are very difficult to resolve with feed-forward current AI systems. And for those specialists, some of these principles, they are exploited in reservoir computing and in liquid state machines, but they are not mainstream artificial intelligence systems yet. To give you a brief example of what happens in such a recurrent system, imagine a pond of water, and somebody throws objects into that water, stones of different size, at different times, at different locations. The result will be that each of these events creates a propagating traveling wave, and these waves interfere with one another, creating a very complex high-dimensional interference pattern. But one can show that if one puts a few sensors into that pond that measure amplitude, frequency, and phase of the waves, one can reconstruct precisely the sequence of events, because this water pond has a memory. As long as the waves propagate, information is maintained. And it so happens that recurrently coupled networks have exactly the same property. Here's an example of a recurrently coupled network with the nodes being reciprocally interacting. If one disturbs one or two of these nodes by an input pattern, there will be propagating waves spreading throughout that network in a very idiosyncratic way, because the natural networks in addition have not homogeneous connectivity, but all the connections are adjusted, they are plastic, and they have learned, according to the statistical contingencies of events in the outer world, to couple certain nodes more than others. I have no time to go into details of this, but take this metaphor as a way in which natural systems transform low-dimensional input patterns into very high-dimensional state space, where then classification and linear separation is very easy to be done. They have fading memory, which makes it possible to encode sequences and to superimpose information in the simultaneous state of the network that comes from sequentially occurring events. So what are the dynamics of these recurrent networks? I have already said they provide an extremely high-dimensional coding space, and given the number of neurons we have and the number of connections among those neurons, some people think the dimensionality of such a network can be, or of the dynamics that emerge on such a network can be infinite. I would prefer the picture. Okay. I talked about the fading memory of the dynamics of these networks. Because of the high dimensionality, they can store a vast amount of information. They allow for parallel search and ultra-fast readout. And again, I have no time to go into the details, but this allows natural systems to compare the prior's a priori knowledge with incoming sensory evidence very, very, very quickly, within 200, 300 milliseconds. Every time you change your gaze, you match different sensory evidence with different priors, and this can be read out from this immense amount of stored information within such a short period of time. Again, something that in artificial systems does not exist. Then, because of the high dimensionality, one has very good separations of representations that would overlap in low dimensional space, but can be linearly separated in high dimensional space, which is nice to have it. And because of the fading memory that is caused by reverberation, sequence information can be stored and processed. Very important for language processing, for example. So I skip you the experimental evidence. One can make experiments to test these assumptions, and much of it has actually been confirmed. So we know that information about the cognitive object is distributed across many neurons. They are dynamically associated in assemblies. The networks are dynamically formed as a function of the goal that has to be achieved. We have fading memory. We can handle sequences. Information of subsequent events can be superimposed and be simultaneously available for analysis. And one has virtually unlimited storage capacity in such a high dynamic state space. And most of these features, I think, lack in current AI systems, but I'm ready to learn. Now, what are the limitations of our digital computing strategies in the moment? It's very difficult to simulate analog computations with a digital computer because of the clock cycle. There is no activity-dependent local synaptic plasticity. All the learning has to be done algorithmically with a very, very cumbersome backpropagation algorithm. If those systems were more dynamic, it would be very difficult technically to control the dynamics that emerge from recurrent networks because they have runaway characteristics. There is no dynamic formation and flexible association of components into assemblies. And as far as I know, there is no good solution for the encoding of nested hierarchical relations that you need in order to describe hierarchically structured complex objects. So, another fundamental difference is that AI systems, as far as I know, they lack internal evaluation systems, so they have no ability to judge the consistency of their internal states. They don't know when they are right. They don't know when they have a Eureka event experienced, which we can do without having feedback from outside. Therefore, they have no self-organizing optimization of internal states. Anyway, they can't self-organize well because they have no nonlinearities that would be required for that. And therefore, most of the learning processes are supervised, and they depend on external reinforcement. Unlike learning in our brains, we can capitalize on priors that come from evolution, as I will say in a moment. So artificial systems have to be told whether they obtained a valid result. And here you have the effort that nature made in order to implement these internal evaluation or reward systems. Everything that is depicted here in reddish are those centers in the brain that look at all the activity patterns in the brain and find out whether they are consistent, whether they are coherent, whether they make sense, or whether they are conflicts. So, now, another fundamental difference between natural and artificial systems is, of course, that AI systems, at least as far as I know, they lack the comprehensive model of the world that resides in the functional architecture of the brain and has been acquired both during biological evolution and ontogeny. It's an enormous amount of knowledge about the world that is exploited by brains for their computations. Now, I think in theory, such a model could be installed by engineers by design and through supervised and unsupervised learning in artificial systems. But before this will be possible, I think we would have first to understand a little bit better how nature got there to the implementation of this internal model. And I think we are far from really understanding how that is done, both during evolution and then during real life. And another 2 slides and then I'm done. Even if the optimistic prognosis would hold that we were able to implement a realistic model of the world and all the cognitive abilities of human brains into these artificial systems, I think they would still lack a valid self-model. And this has severe consequences because the self-model, with all its immaterial and spiritual dimensions that we experience as humans, I think are the consequence of perceptions that we humans have, perceptions that are shaped by the priors that we take not from the material world around us, but take from the social and the cultural realities that we have created as humans during the course of cultural evolution. So our self-perception, our attributions of being part of having a spiritual dimension, a mental dimension, an immaterial dimension, this perception that we have from the others and from ourselves is the consequence of a cognitive process, the priors of which are taken from cultural and social realities. So I think that this deficit, I will be done in a minute, could only be overcome if we actually raised our robots like our children and embedded them in the social cultural environment as we are used to do it with our children, given that they have all the cognitive abilities of our children, which is another problem. So I think that we are far from being able to attribute something like consciousness or so to artificial systems, because I see 2 phase transitions in biological and cultural evolution. The first is when neurons assembled make complex brains and you get cognitive agents as a result, with all the cognitive abilities of human subjects. It's a different ontological level. It's our behavior. And then there has been another process where these cognitive agents, that's on the right side, start to interact with each other, creating social cultural realities. These in turn shape our experiences and act back on our self-understanding and our self-model. And only if robots succeeded to go through both phase transitions, I think we would take them seriously. So since they have not achieved either phase transition so far, and should they ever get to the first phase transition, they still would have to go to the second one, which I think is a difficult one to overcome. And therefore, my conclusion would be, they have no spiritual dimension, they have no meta-awareness, they have no self-consciousness, they have no self-model, they have therefore no ethical responsibility, no morality, they have no qualia of experience and no moral value. And that's my conclusion. Thank you.